Newton's law of cooling describes how the temperature of an object changes as it interacts with its surroundings. At its heart, the law states that the rate at which an object loses heat is directly proportional to the difference between its own temperature and the temperature of the environment. Imagine a hot cup of coffee sitting in a cool room. Because the temperature difference is large at first, the coffee loses heat very quickly. However, as the coffee cools down and its temperature gets closer to the room's temperature, the rate of cooling slows down significantly. This relationship implies that cooling is not a constant process, but one that changes dynamically based on the thermal gradient between the object and the ambient air. This fundamental principle allows us to predict how long it will take for something to reach a stable temperature. When we express this law mathematically, we say the rate of change of temperature with respect to time is equal to a negative constant multiplied by the temperature difference. That negative sign is crucial because it indicates that the temperature is decreasing over time. The constant, often represented by the letter K, is a specific value that depends on the unique characteristics of the object and its environment. For example, a metal spoon will have a different cooling constant than a ceramic mug, because materials conduct heat at different rates. By solving this differential equation, we find that the temperature of the cooling object follows an exponential decay curve. This means the object approaches the room temperature rapidly at first, then more and more slowly as time goes on, creating a distinct curve on a graph. While the temperature difference is the primary driver of cooling, several other factors influence the constant K in our equation. The surface area of the object plays a massive role. A flat, spread-out piece of dough will cool much faster than a thick, round loaf because more of its molecules are in direct contact with the air. The nature of the surrounding medium also matters. If you place a hot object in water instead of air, it will cool much faster because water is a better conductor of heat and has a higher heat capacity. Even the movement of the air, such as a breeze from a fan, can increase the cooling rate by constantly replacing the warmed air near the surface with fresh, cool air. This is why we blow on our food to cool it down more quickly, effectively increasing the rate of heat transfer through forced convection. It is important to remember that Newton's law of cooling is an approximation that works best when the temperature differences are relatively small, and the primary mode of heat transfer is convection. If an object is glowing hot, it might lose more heat through radiation, which follows a different physical law entirely. However, for most everyday scenarios, the exponential model is incredibly accurate. On a graph, you would see the temperature line curve downward, getting flatter and flatter as it nears the ambient temperature line. Theoretically, the object never perfectly reaches the exact temperature of the room, but for all practical purposes, it eventually reaches a state of thermal equilibrium. Understanding this curve helps forensic scientists estimate time of death, helps engineers design better cooling systems for electronics, and even helps meteorologists understand how the ground cools at night.